Hi guys, so I'm Vitaly Gordon. I lead data science and engineering for Salesforce Einstein. And I think Alexei might kind of a little bit oversold me about he likes to, I still occasionally when my developers let me write code, and I think Alexei kind of took it too far and said, Vitaly, I want you to, to start this conference, I want you to keynote, I want you to do live coding, and I say, okay, no pressure. So here I am. Please expect some stuff to break. I will be like jumping between a lot of windows. And so if something doesn't work, at least you guys know it's real. So without further ado, this is the talk about artificial intelligence for the 99%. And this is about also what we're trying to do in Salesforce Einstein. I will not talk about, because again, my talk is not to kind of represent the work that my team is doing, but more like what I personally passionate about, and it's kind of bringing whatever we're going to discuss today to a larger mass. I'll start with a rant. And the rant is, it actually came from how many of you here maybe heard of Aguirre Zimnes? He used to be at Twitter. He was one of the authors of Scalding. Okay, not so many, but some of you do know, and he had this rant over the weekend about data science, machine learning, everything in between. It was like a very long tweet storm, and one of the things he said there is like, deep learning is kind of irrelevant for 99.99% of the problems out there. And I didn't post the tweet because, again, there will be a recording of this, and I'm not necessarily, want to represent, because I do not necessarily agree with that statement. However, I did find it funny that if you look at today's schedule, you can see that some words are fairly common in all the sessions. So if it's hard to see what exactly the word I'm referring to, I did a word cloud for you. So, deep learning. By the way, I'm not here to bash deep learning. Deep learning is great. Part of Salesforce Einstein. We have required MetaMind as well. Stephen Murray will be here later this day. I think Richard Socher goes and talks on the third day of the conference. We all love deep learning. And, and this conference is great because it tries also to bring the applied kind of value of deep learning and not just kind of the theoretical, but still it kind of feels like the clip that I'm about to show you. When I made the clip, it was like from a show that I personally love very much, but then I realized that maybe it's actually not reaching as broad of an audience as I thought. So just with a kind of show of hands, how many of you know Top Gear or the new kind of, okay, it's more than a thought, then great. So here's thing number one that I hope the sound will work.
Quite a few complaints that we don't feature enough affordable cars on the show. So we're kicking off tonight with the cheapest Ferrari of them all.
So if you didn't get the joke, it's Top Gear is usually about cars that regular people cannot afford. So, and a lot of people complain about it, and then Top Gear kind of said, okay, we're kicking off the show with the cheapest Ferrari of them all. And kind of this is what I also kind of feel a little bit about, kind of these. A lot of the talk about deep learning is kind of the version of the, especially the applied ones, about the cheapest Ferrari of them all. That ends my rant. So what is the problem? Like why did I decide to talk about it? And it's a lot to do with kind of the work that we're doing and we're seeing. It's not, again, it's not that there is a problem with deep learning, but something I've experienced myself coming from, I was previously at LinkedIn, which is one of these classic Silicon Valley kind of tech companies. And now I actually, at my work for Salesforce, I get to meet with a lot of, so Salesforce has hundreds of thousands of customers across the world, and we work with all of them. And in terms of most of these customers, when you meet with them and talk about their machine learning application, it feels a little bit like Manhattan in the 19th century. So the problem is, talking to these companies about the latest events in deep learning is kind of like, having Elon Musk show up and talk about Hyperloop when people, ride horse-drawn carriages. So it's great. It's interesting. Hyperloop is amazing. SpaceX is amazing. Occupying Mars is amazing. But there is more to be said. But some of you might say, well, Vitaly, we are in the age of data. There is so much data is generated. There is zettabytes, yottabytes, and brontobytes, and gigabytes, and IBC projects. Like, surely, we have a lot of data, and everyone can benefit from that. And yes, and this is like why I don't, not a big fan of a lot of these kind of analysts. They take a very, very simplistic view. Yes, the amount of data is growing, whatever percent was created, whatever the last years. I get it. But now ask yourself, for kind of machine learning purposes, or the sexier name, AI, how much of that data is actually labeled and could be useful? So let's talk about one of the largest labeled data sets that we have today to work with. It's ImageNet. And as you can see, the total number of images in ImageNet today is roughly 14 million images. There's the YouTube 8 million data set, which, funny enough, and I take it from the YouTube 8 million data set contains 7 million videos. I think it's, they chose the title in order to show some progress, or, so they will have room for growth there. They didn't want to commit that it will stay at 7 million. So it has 7 million, it has like, 3.4 average labels for video. You can do the math. It's around, 25 million labels. Again, an amazing data set that, a lot of the latest advances in artificial intelligence run videos come from having that data set. Here's another one. The Amazon reviews data set, and again, 35 million number of reviews, 7 million users, products, a bunch of users with reviews. You get it. So I guess the point I was trying to make here is, even though the amount of data grows exponentially, as you can see, actually, these data sets are extremely hard to come up with, and they all, in the millions, which is, again, it's way, way bigger than what we used to have. But still, it's not so much the exponential growth, and a lot of these data sets actually have not been, growing as fast as all the other data sets. And if you actually take all of them, we talk about the age of big data, it's actually, I looked at the file, all of them combined can fit on my iPhone. So that's kind of the age of big data that we're talking about. So the second kind of problem with, let's say, artificial intelligence and the state of the world today is that we kind of, we talk about deep learning, and this kind of assumes that shallow learning, and this is kind of the term I will use for, let's call it, classic ML, that this is kind of a solved problem. That, everything that we could have solved already with traditional machine learning techniques have already been solved, and, it's time to move on to solve kind of the next problems. And again, from our experience with working with a large myriad of companies, this is not true at all. This is not even close, to be honest, for us to solve kind of all these problems, to move to the next stage. So here, I'll do a short demo that hopefully will explain kind of what I mean by kind of shallow learning is not solved. And this will be an extremely trivial machine learning application that, let's see if it switches. Can we switch to screen somehow? from here. Terminal. Or am I doing something wrong? Okay, let's. Oh, let's see. And, okay, and let's see. Well, sorry. Oh, well. Is that, wow, it's very small. Okay. Is that big enough to see? Okay, so the logistical regression library, okay? And yeah, how can I maybe do the screen a little bit? Well, never mind. So first of all, what I want to show is the train function of liblinear. So look at how many parameters it has. So first of all, there is the type of solver, and as you can see, there are 8 different solvers for just logistical regression, and some of them are L2 regress, some of them L1. So probably most people are in the room either find it trivial or have no idea what I'm talking about, and that's fine because kind of the point is there are a lot of parameters. That's what I'm trying to say here. And then there's the kind of cost, there's the cost parameter, and there's the 2 epsilon parameters. There's a bias parameter, there's a weight parameter, there's some cross-validation, and these parameters are, there's the these 2 are not so much about the actual algorithm, but more with output and stuff like that. The point is, people assume that machine learning algorithms are kind of like quicksort, right? It's a deterministic output that you just give it an input and it will find the best solution without realizing that, oh, actually, we have a bunch of knobs. So that, you might ask yourself, but how important these knobs are? So in order to actually show, I'll take an extremely simple kind of data set that was like published in the 90s or something like that, and hopefully you can see here. So it's called the adult data set. It's trying to predict whether it's based on kind of a demographic data and socioeconomic data, whether the person's income is above 50K a year or below. And as you can see, there's like age, work class, their education, marital status, occupation, race. So again, the point here is not so much about that data set, but kind of trust me on this, that this is an extreme representation of a trivial data set, okay? So, and kind of I think there is like capital gain, capital loss, and again, just the way this data is pre-processed, there is only 14 features, but we will find like more than 100 features because what they did here is on the continuous data set, they just broke it to quantiles, and all the categorical were basically one-hot encoded, which basically means is like, for every single, for example, country now becomes a binary variable that is either 1 or 0, whether that person lives in that country. So let's try to kind of train a classifier to predict that data set. So first, let's kind of start with, sorry, this is, so just, I have some, so I also kind of took this data set, and there's like 9 different representations. Each of them has slightly different amount of positive, but it's all from the same data set. You can see that in this A1A, which has 1,200 negatives and 400 positives. So in this kind of data set, let's just train a classifier, and I will use the first kind of solver, and I will use the C parameter, which is actually goes through all the possible lowercase c parameters, not all the possible, but many of them, and tries to find the best for this data set. So for this is A1A, and as you can see here, it tries different C parameters, and you can see here kind of that based on that single parameter, you can actually find that there's quite a difference between the accuracy of the algorithm applied on this extremely trivial data set. It ranges anyway from, doesn't matter what rate it is, but from 75 to like 83.7. So just by tweaking one parameter, we can actually, kind of get a fairly poor, even though say 75 is not so poor, but again, it's a trivial data set. So to something that is a little bit bigger. And you can see here that the best C is kind of 1, which, as you can see, the log here corresponds to, is 0, and this is kind of the best. So same data set, same exact data, but let's just try a slightly different solver. And as you can see here, suddenly, actually, it changes, and the best C is now something else. So again, the point here is trivial algorithm, trivial data set, same exact data set, two completely kind of different, like two different tweaking of the same kind of knob that gives us different results. So, and then let's take the same kind of data set, but maybe a little bit larger, which is the A9A, which I think is the full data set. You can see here, there's 24,000 negatives, about 8,000 positives, and we're going to try, again, the same one. Again, it's the same data set, just more labels. As you can see, because there is more data, it's slightly slower. And again, now the C is 2, and if we try a different solver, we'll get, again, now the C is 0.25. So, but you might ask, kind of, okay, but and this was, again, I didn't actually touch the data set. I was just trying different configuration of the solver. Like what are kind of common techniques that people might do is say, okay, whenever I showed you guys now the positive negative label count, something that data scientists do is, for example, we can upsample or downsample the data. And let's, see how it might affect our data. So I have this, kind of a very simple script, Python script that just does, hey, let's upsample the +1 means positive by 3 times, so we'll get like roughly 50-50 correspondence, and then, let's write it to A9A.U stands for upsample, and let's just make sure that we upsample correctly, and as you can see, it's roughly 50-50. And then we can, run the same training on the upsampled data. As you can see, actually, what's interesting about is actually the lowest now rate is actually higher than the lowest before, but the highest is actually kind of lower. And now we have kind of similar C, but it's actually, it looks like in the cross-validation, we actually made it worse by upsampling. And again, people that don't really understand what all these knobs are, and they say, okay, if by upsampling, we actually hurt the performance, maybe I need to downsample. So, let's try it. Let's see, if we downsample the negatives, like by 100 times, and write it here, and again, now just to show that the distribution is now, sorry, I did something wrong. What did I do wrong? No, I wanted to actually downsample the, okay, something is, okay. Something is not, oh, sorry, yes, my bad. Yeah, that's the wrong part. Yeah, okay, so I just removed 99% of the positives, and now if we train again, okay, yeah, we have it here. Success, 99% cross-validation accuracy. As you can see, you should always downsample. So hopefully you're laughing and you just understanding that this is not true, but what I'm trying to, again, if from all of that demo, the main takeaway is just how unintuitive this kind of machine learning is. And this is, again, a trivial example, right? It's like I try it on different things, and I'm saying, okay, computation is infinite. We can, just brute force through all of it. And, I just empirically test. I don't need any theory. And, this is kind of the results, right? I try technique. I get, 99% accuracy and say, okay, work. And I'll spare you the detail. I also have a test set that, we didn't train on. And, just trust me that if we try the model I just trained on the test set, it will not do very well. In other words, it will overfit. So this is kind of my point, if we go back to the PowerPoint, that this whole shallow learning as being a solved problem for the 99% is also not actually true. But the biggest problem of them all is kind of how do you take the kind of cute demo I just did and make it to actually a real viable product. So a lot of the companies that kind of we deal with are real companies with real products and real customers. So actually the quality bar is as high as any kind of Silicon Valley company in terms of what they need to get into production. However, and this is kind of a favorite slide of mine that I show pretty much at any internal or external talk that I give, that is from a Google paper that's called the Hidden Technical Debt in Machine Learning Systems. That you can read it, and anyone here that ever tried to take a machine learning product into production probably recognizes every single box here. It probably knows that it doesn't matter what is kind of your parameter that you count the size of the box, the line of codes, time spent, engineering hours, whatever you want. The black box is actually small. It doesn't mean that the black box is not extremely important or extremely sophisticated. All of that doesn't matter. There's like, in real system, there's just a lot more stuff that needs to happen. And this is also where we find our customers probably fail the most. Because honestly, the cute demo that I did, you can find a kind of bright student from a college, just get them to your company, even from companies in this flyover states, as we call them, and they will be able to do something at a POC level. But actually taking it into production, supporting kind of millions of real customers, that's a problem. So the question is, like, why should we care? And I kind of touch upon it. And this comes also from the personal experience after working at LinkedIn and doing a great job that got me promoted, which is kind of improving our job recommendation algorithm by 2%. I worked on it for a year. And the point is, like, most companies are not Amazon, Google, or Facebook. These companies are great. They're, I love their products, and honestly, when I was a data scientist, I felt working at LinkedIn, even if you fire every single machine learning engineer or data science at this company, I'm not saying like just, remove their work, but keep the work that they did and like never let them improve any of it again, these companies would still have great products. The problem is, what about the other 99% of the companies? Think about your healthcare provider, about your bank, about your insurance company, about your insurance providers. These companies, it's kind of mind-blowing that they probably even have more data about you than some of the companies I mentioned or some of these Silicon Valley companies. However, they actually kind of fail to do much with it. Like whenever I log into any one of these providers, this experience feels like, oh yeah, they're seeing me for the first time, even though I might be a customer for a decade now, right? So this is kind of the problem that we're trying to solve at Salesforce Einstein, and kind of, but what is the problem? Like, why is it so hard to solve kind of that problem for these companies? A, there's more of them. Usually, it doesn't matter what pie you're looking at, 99%, more than 1%. The other problem that we have, especially at Salesforce, is we care about privacy a lot. And when I say we care about privacy, everyone cares about privacy. I get it, but let me tell you why we care probably more. Salesforce itself was the first cloud company, so think about it, it's like not in the year 99 when Salesforce we're now celebrating 18 years, so yes, it's 1999, is telling like a lot of companies, put some of your most sensitive data in this thing that everyone gets it, the cloud, right? But then it's basically the cloud, which is someone else's computer. Put your data, and when I talk about sensitive data, if you're a public company, the business transactions and how many deals you won or lost are basically can be used in order to know how you ended the quarter. It can be easily used to, it's not even predicting the stock market, it's fairly obvious what this company. So for us at Einstein, actually, even the data scientists do not look at our data. All of the work that we're doing is without actually looking at the customer's data. And again, there's hundreds of thousands of them. The second problem is performance matters. Why performance matters? Again, it's like this obvious statement, but let me try to give you the analogy. In a consumer internet company, if you improve, like, if you have an algorithm and you improve it for 90% of your customers, that's a huge deal. It's a huge success. You'll get promoted, and you will be celebrated. With us, every single customer pays us for that service. For example, I cannot go to Acme Corporation and tell them, hey, sorry, but it works for the other 90%, but I still want to collect your check. It doesn't work this way. It has to work for every single customer, or we're not getting paid. And the third problem, which is probably the most difficult, is we have different type of beasts. We have huge customers, and we have tiny customers as well. And all of these customers, and here I'm mostly talking about, let's say, volume of the data. It's not like their market cap. So a company like Fitbit might be smaller, but because it's something I didn't mention, we also have an IoT business. So like, for example, IoT generates way more data than some other businesses that some other products but the point is we have to support all ranges and all use cases of data. So because I'm kind of running out of time, I will jump very quickly to demo, and this is an exciting moment because this is kind of you seeing it before most of the company have seen it, and it will be a very small sliver of the thing that we're doing in order to solve our problem, but hopefully it will just give you a rough idea of what does it mean to build machine learning products for hundreds of thousands of customers of different sizes without actually looking at their data. So hopefully it will work. Okay, so let's jump to it. Larger, larger, larger. Is that big enough, or should I make it larger? Okay, awesome. So this is we have our biggest business unit is Sales Cloud, is our CRM product. And here, let me just, check out. So, okay, so I just checked out my branch, which is my code, and I'll jump right quickly. Let's do it into presentation mode. And so this is what the code looks like. It's something that we call internally Optimus Prime because it's a bunch of transformers, and we gave a lot of talks about it, and hopefully you can see. So what is Optimus Prime is we call it metadata modeling language. So we have here basically, this is just definition of what is the data, what is the workflow, what evaluator we use. And this is the cool part because what I'm about to show you is actually similar to TensorFlow, is a computational graph. You can say any node in that graph you want to compute up to that node, and this is what this represents. Okay, yeah, how do I jump between tabs and this presentation mode? Sorry, guys. Okay, so first of all, and by the way, the cool thing about it is we also have like this beta mode for Optimus Prime, that the code you see can be also kind of auto-generated. So you can input, kind of input the customer and their data, and that will generate. So here's a bunch of kind of features around specifically one of the Salesforce object. So something to know about Salesforce. Salesforce has a very kind of a well-defined schema that is, all the Salesforce customer uses, but that schema is used by many, but also can be customized. So here you can see some of the fields that we have. Most of the Scala code is around values, so like ignore in the extract function. But some cool things I can show here is like if you see the phone number, sorry, it's for some reason, oh, it's the old, but we also have, kind of a phone type, so I guess this did not recognize it as a phone, but it can be also a phone that we can then do some cool stuff with it. And the other part of it is actually, you see there's also custom fields, which are fields we actually don't know, and every customer has a different set of these fields in their schema. And basically, as you can see, we actually treat them as this key value map type of transformation for all of them. So now we'll see very quickly what are those how this computation graph looks like. And again, because I don't know how to switch, I'll go this. So here's the actual code. So the code that you will see, it's not a DSL. It's actually it's a DSL, but it's a library. It's written on top of Spark ML. But what's great about it, because I said we have customers of all sizes, that code can be executed as a Spark job, as a Spark batch job, as a Spark streaming job for real-time purposes, and also on a single machine for the smaller customer that it kind of doesn't make sense for them to have this code run on, on a cluster. And this is honestly like 80 or 90% of the customers out there do not require the utilization, but that code is extremely defensive also on the performance side. And what I'm about to show you is also on the modeling side. So basically, you can see here we do a bunch of features. So here the pivot top K is basically one hot encoding with the top 20 being their own, and then the other, everything else falling in the other bucket. Description, this is kind of cool. You can see the valid phone here is actually, because we recognize it's a phone type, then we can now do, in code completion, say is valid phone, like things like that, and is valid phone with the context of the country. So basically, there is a rich text system, and we can have a transformers like Jacquard similarity on top of it, and then we put all of it like in a feature vector. And sorry that I'm running through this, just running out of time. But the point here is also, this is kind of where a lot of the magic happens, is we automatically remove bad correlated features with low entropy, and I'll just show you the results. And here we also apply a bunch of different models. Here, as you can see, there are actually 4 models that we try. It's logistic regression and random forest, but the logistic regression, as showed, has 2 params, and the random forest has 2. In this case, it's actually kind of doing grid search because there are like very few params. But in cases where there are a lot of params, and even it's not only the kind of hyperparameters of the algorithm, but also the parameters inside the feature transformation, it can be smarter than just grid search. So basically, I'll skip the step while I kind of input this, but the way we do it, sorry. So the way we actually execute it, as you can see here, it found the way we work, because we have all of these different tenants. Like I said, we actually here found that we have 10 different customers, and again, this runs on my local Docker, but in our kind of staging and prod environment, it will run on all of them. And as you can see, there's the IDs of either Spark jobs or whatever job it is. It will actually, the one piece of code will run on all of the customers at once, and you can collect metrics. So what kind of the metric look like, and this is kind of will be last thing I show. So this is kind of a Zeppelin that we use, and again, this is in order to, no one actually has any data on their laptops. I hope you can see some of the things here, and kind of the point the main point here, as you can see, for this is one customer that these are all the fields that were dropped. As you can see, some of them are custom, and some of them are actually standard fields that were dropped. And this is the interesting part. Here it actually tried 4 models. As you can see here, the logistic regression models actually outperformed the random forest model. And because here the positive labels were very low compared to negative, the data set was both upsampled on the positive and downsampled on the negative. And the next customer that here I'm showing, and by the way, these are real results from our kind of production environment. Here you can see a completely different set of fields were dropped. And as you can see here, actually it's interesting here, the random forest models actually way better than the logistic regression models. And again, in production, tries more things, and we're now integrating it with flow-based algorithms as well. So I think this is about all I had for today. Sorry. So I just wanted to say thank you, everyone. And if what I talked to you about is interesting, you found it interesting, so please reach out to our recruiting team upstairs, or just to me personally at Vitaly@salesforce.com. So thank you.